Hello, everybody, and welcome back to Abstract Algebra. Plan for today is we're going to finish off our discussion of Chapter 13 by continuing to discuss the relationship between integral domains and fields. And then we're going to start moving into Chapter 14, looking at different types of ideals. Specifically, what does it mean for an ideal to be prime versus what does it mean for an ideal to be maximal and other such things. I've got my usual office hours coming up on Monday, 10 to 10:50, 2 to 3. Remember, this is for Friday's class. And as far as homework goes, if you're watching this on Friday, you better be prepared because exam 2 is due tonight. If you're watching this on Thursday, it's due tomorrow night. Where do they put mathematicians who commit crimes? They put mathematicians who commit crimes in prism so that they can be with all the other convex. Okay, so let's have a quick reminder of what we were talking about in this packet. So if you recall, we were talking primarily about integral domains versus fields. An integral domain is a ring where multiplication is commutative, it has a multiplicative identity of 1, and no zero divisors, meaning in an integral domain, anytime you multiply two things together, a times b, and get 0, it has to be the case that at least one of a and b are individually equal to 0. So if ab equals 0, a equals 0, or b equals 0. A field is very similar in that it has the same first two properties, that multiplication is commutative, r is a multiplicative identity, but the third property is different, and then in a field, every non-zero element has to be a unit, meaning every non-zero element in your ring has to have a multiplicative inverse. So given any r not equal to 0, there has to be some element r inverse such that r times r inverse is equal to 1. And we talked a little bit last class about some of the relationship between integral domains and fields. In particular, we said Z mod NZ is an integral domain if and only if it's a field. So for Z mod NZ, integral domain and field mean the same thing, both of which are true if n is prime and false if n is not prime. So for Z mod NZ, it's an integral domain if and only if it's a field. However, we've seen that that's not true in general because the integers, for instance, make up a ring that's an integral domain but not a field. Integers have this property of no zero divisors. If you multiply two integers and get 0, one of the integers had to be 0. But it doesn't have this property that every non-zero element has a multiplicative inverse. Most integers, in fact, every integer other than 1 and minus 1, say 2 for instance, 2 does not have a multiplicative inverse in the ring of integers. There's no integer you can multiply 2 by to get back to 1. And also, at the end of last class, we showed that every field is an integral domain. That any ring that satisfies these three properties is going to satisfy these left three as well. If you have all non-zero elements are units, then no non-zero elements are zero divisors. And so today, I'd like to go the other way around and see, can we prove under which circumstances will integral domains have to be fields? It won't be all the time, because the integers are one but not the other. But are there some circumstances under which one but not the other ends up working? Before we prove that, though, I'm going to prove a lemma related to integral domains. And that's going to be this, that in any integral domain R, if a times b is equal to a times c, and a is not equal to 0, then b has to be equal to c. So in any integral domain, as long as you multiply a times the same thing and you get ab is equal to ac, unless a is equal to 0, in which case ab and ac would just both be 0 no matter what your b and c were, if a is any element other than 0 in your integral domain, ab equals ac has to imply that b equals c. And in fact, this is going to be the cancellation property of integral domains. Because this is something we could do in group theory all the time. Say, oh, AB is equal to AC, therefore B is equal to C. Well, in integral domains, you can always do that, assuming A is non-zero. But in an arbitrary ring, it turns out this cancellation property does not always work. Don't believe me? Well, turns out I can give you an example. In non-integral domains, cancellation may not work. So as an example, let's take a look at the ring R is going to be Z mod 12Z, which, since 12 is not a prime number, Z mod 12Z is not going to be an integral domain. Also not a field, but not an integral domain. In this ring, I claim that 2 bar times 4 bar is going to be equal to 2 bar times 10 bar. Why is that? Well, 2 bar times 4 bar is 8 bar in this ring. And if we were to take 2 bar times 10 bar, well, 2 times 10 is 20, and 20 mod 12 is going to be equal to 8. So in this ring, 2 bar times 4 bar will actually be equal to 2 bar times 10 bar, but can we cancel out 2 bars from each side and say 4 bar has to be 10 bar? No, 4 bar and 10 bar are not the same in this ring. Not 2 bar. 4 bar is not equal to 10 bar. So in this ring, you can't cancel out 2 bars from each side and say 2 bar times thing equals 2 bar times other thing, therefore first thing equals second thing. Doesn't quite work. It works in an integral domain, but not in an arbitrary ring. So let's see if we can actually prove this lemma is true over an integral domain. I'm going to go ahead and erase this in just a sec, so pause the video if you need to write any of that down. So here's our proof that cancellation works in an integral domain. So first of all, we're going to assume that if R is an integral domain, A, B, and C are elements in R such that A is not equal to 0 and AB is equal to AC. So we have all these different pieces. We're working over an integral domain. A is non-zero, and A times B is equal to A times C. And our goal is going to be to prove B and C have to be equal. Well, if AB is equal to AC, then I claim 0 has to be equal to AB minus AC, right? You can just subtract AC from both sides of this equation, and you'll be left with AB minus AC is 0. So now, I'm going to factor out an A from this expression and say AB minus AC is equal to A times the expression B minus C. And here, I'm using the distributive property, which is a property that has to be true in every ring by definition, hence in every integral domain. So now we have 2 things that we're multiplying to get 0. A and B minus C. And now we can say that since A times B minus C is equal to 0, and A is not equal to 0, thus B minus C has to be equal to 0. So why is that? Well, in an integral domain, remember we have no 0 divisors, meaning anytime you multiply 2 things in an integral domain and get 0, it has to be the case by definition that one of the 2 things you're multiplying together was 0 to begin with. Well, here we're multiplying A and B minus C to get 0. We assume A is not equal to 0, so that forces what's left, B minus C, has to be equal to 0. Otherwise, we have non-zero things multiplying to give us 0, which would mean we have 0 divisors, which would mean we don't have an integral domain. So B minus C is equal to 0, and thus adding C to both sides tells us B is equal to C. So in any integral domain, we're always going to have this nice cancellation property we had from group theory. Or the one exception you have to keep in mind is A has to not be 0 for this to work. Otherwise, you could say something like, well, 0 times 2 is equal to 0 times 3, therefore 2 is equal to 3. Nah, that's nonsense. Doesn't work out that way if A is 0, but if A is non-zero in an integral domain, AB equals AC implies B equals C. All right, so we proved our lemma. So next up, I want to prove the main theorem for today. And that theorem is going to be the one that tells us why does Z mod NC have to be an integral domain if and only if it's a field, but the integers can be one but not the other. In this theorem, get a better place to draw. This theorem is actually going to say any finite integral domain is a field. So every field is always going to be an integral domain regardless of how many elements are in it. If you're looking at a finite ring, then field and integral domain are if and only ifs. You have a field if and only if you have an integral domain. If you're looking at a finite ring, like Z mod NZ. But if you're looking at a infinite ring, like the ring of integers, it's possible to have one but not the other. So let's see if we can prove this, that every finite integral domain has to be a field. So to start off, we're going to let R be a finite integral domain. And then R automatically has to have the first two properties of being a field, because multiplication being commutative, R having multiplicative identity 1, true of both integral domains and fields. And multiplication is commutative, and R has multiplicative identity of 1. So next thing I'm going to do is I'm going to let little r in R be some non-zero element. And what I want to do is I want to consider the sequence of elements r squared, r cubed, r to the fourth, etc., going on forever. Meaning, I just want to keep taking higher and higher powers of r. Where r, we haven't really used this notation much, but r squared, r cubed, r to the fourth just means r times r, r times r times r, r times r times r times r, yar, etc. Here's something to keep in mind. Since R is a finite ring, this sequence eventually will have to repeat itself. There's only, say, n equals 10, or n equals 50, n equals 1 million elements in the ring to start with, some finite number. It's impossible for all of these elements in the sequence to be distinct from each other. There has to eventually be some repetition. So in other words, we can say, since R is finite, this sequence must eventually repeat. So that, in other words, r to the I has to be equal to r to the j for some I greater than j. So for some power r to the I and some other power r to the j, assuming I is greater than j without loss of generality, r to the I and r to the j will be equal. If this never happened, then the ring R would have to have infinitely many elements in order for this sequence to never double back on itself. itself? Well, if r to the I is equal to r to the j, that's going to then tell us that r to the, how do I want to write this? R to the I minus j times r to the j is going to have to be equal to 1 times r to the j. Why is this? Well, the left-hand side is equal to r to the I minus j times r to the j, just going to simplify to r to the I power. 1 times r to the j is going to be, well, just r to the j. And now, notice that we have an expression of the form AB is equal to AC. And here's what I want you to notice. R to the I minus j times r to the j is equal to 1 times r to the j. R to the j is not 0. Why is r to the j not 0? Well, that's since r is not equal to 0, and r to the j is equal to r times r to the j minus 1, which, if these are both non-zero, since we have an integral domain, r times r to the j also can't be 0. What if r to the j minus 1 is 0, Dr. Gerstle? Well, then replace r. Well, then we can replace this with r times r to the j minus 2, and just keep going downward from there until we eventually end up with just r's here. So, we know r to the I minus j times r to the j is equal to 1 times r to the j. Since we're working over an integral domain, we have this nifty cancellation property that we just talked about in our lemma that'll tell us we can sort of cross out r to the j from both sides, and we'll be left with r to the I minus j is equal to 1, which in turn will imply that r times r to the I minus j minus 1 will be equal to 1, and so r inverse will be equal to r to the I minus j minus 1. Because we found something that if you multiplied by r, namely r to the I minus j minus 1, we would get something that's equal to 1. And so the multiplicative inverse of r has to be this expression. Thus, all non-zero elements in R, all non-zero elements in R are units. So R is a field. And this shows that any finite integral domain will have to be a field, which automatically will tell you things like Z mod nz is an integral domain if and only if Z mod nz is a field, if and only if n is prime. So Dr. Gerstle, what goes wrong if we're looking at an infinite integral domain? Well, if we're looking at an infinite integral domain, like the ring of integers, then this list never needs to repeat itself. So if, for instance, we had something like r equals 2, then this would become 2, 4, 8, 16, ... The list would never repeat itself, and so you would never have to have r to the I equals r to the j for some I greater than j. So that's where this proof would break it. And that's going to do it for this packet. For finite rings, integral domain if and only if field. For an infinite ring, if it's a field, it has to be an integral domain, but not necessarily vice versa. How are you doing? Only 19 minutes. Okay, so next thing I want to do is I want to start the next packet, which is going to be a packet talking about different types of ideals. We've seen this notion of ideals come up before in looking at quotient rings. They're like the ring equivalent of a normal subgroup, things you can quotient out by. In this packet, though, we're going to go into greater detail looking at different types of ideals and how can we classify ideals. And eventually, at the end of this packet, we're going to end up with another nifty proof that all fields have to be integral domains, but not vice versa. So to start with, let's do a quick recall here. Something I want you to recall is that an ideal S of R is just a subring of R such that if little r is any element in big R and little s is any element in big S, R times S and S times R have to be elements in S. In other words, ideals are just these subrings where if you take anything in the ideal and multiply by anything in the ring, whether or not it's in the ideal, you'll still always end up with something back inside the ideal. Just like with the integers, if you look at nz, you take multiples of n. If you take any multiple of n and you multiply by any other integer, you're still going to have a multiple of n. So I want to start by talking a little bit about a interesting little theorem that relates to units, things with multiplicative inverses and ideals. And what this theorem is going to say is that if R is any commutative ring with a multiplicative identity 1, and S is an ideal in R, if S contains any unit in R, then S has to be the entire ring R. In other words, as long as S contains any element that has a multiplicative inverse, S automatically will have to be the entire ring. So let's see if we can prove this. So let's suppose little s is an element in big S, where little s is a unit. And our goal, since S is an ideal, is going to be to show that S has to be the entire ring. Well, then S inverse automatically has to be an R. Doesn't have to necessarily be an S right away. Saying that S is a unit just means that S has some multiplicative inverse in the ring at large, in R. So S times S inverse, which is just going to be 1 by definition, even if S inverse isn't in S, 1 is going to have to be an element in S, because we're taking something in our ideal at S times something in our ring. Whether or not this element S inverse is in the ideal or not, anything in the ideal times anything in the larger ring has to be in the ideal still. So if big S contains any unit, it has to contain the multiplicative identity 1 to start with. And now we're going to let little r be an arbitrary element in big R, and we're going to show that little r has to be in the ideal S. Well, if little r is an element in big R, then we could take 1 times r, which will be equal to r by definition, once the multiplicative identity. But what's this? 1, we now know is an element in our ideal S. R is an element in R. And even if we're multiplying just by 1, by definition of an ideal, anything in the ideal times anything in the ring is going to have to be an element in the ideal. We just showed that any arbitrary element in our ring has to be in the ideal, because anything in the ring we can multiply by something we can multiply by 1, which doesn't change anything, but since 1 is in the ideal, 1 times r, i.e. r, has to be in the ideal as well. Thus, R is a subset of S, so R and S are equal. Everything in R is contained in S. We already know everything in S is contained in R because S is an ideal, and ideals are by definition subrings of R. So since everything in the ring is contained in the ideal, and everything in the ideal by definition has to be contained within the ring, S and R have to be equal to each other. So just as a quick example, we could say the following, is that, let's say in the integers, the ring of integers, any ideal containing 1 or -1, which keep in mind are our two ideals in the ring of integers, has to be all of Z. Any ideal containing 1 or -1 has to be the entire ring of integers. Luckily, the main ideals in the ring of integers, NZ, those do not, NZ is never going to contain 1 or -1 unless n equals plus or minus 1. So that's usually not something to worry about. But here's another interesting question, and something I want you to think about. Let's look at ideals in the ring of all real numbers for a sec. How many ideals does this ring have? Well, if S is an ideal in R, one of the following must occur. The first option that can occur is that our ideal S is literally just the trivial ring. The subring containing 0 and nothing else. That's one possibility to have an ideal in the ring of all real numbers. It's just S has nothing in it but the additive identity. S is boring. The other possibility is S contains at least one non-zero element, R. So either S has nothing but 0 in it, or S has at least one element not equal to 0. But if R is not equal to 0, then since the ring of all real numbers is a field, R has to have a multiplicative inverse. So that means S contains a unit, namely R, because anything non-zero in the ring of real numbers is a unit, because real numbers are a field. But if S contains a unit, we just proved S has to be the ring of all real numbers. So we just showed that the ring of all real numbers contains only two ideals. Peace. Two ideals, namely the trivial ideal and the entire ring. Thus, we can say in any field R, our only ideals are the trivial ideal, the subring containing only the number 0, and R itself. Any ring that's a field will only have two ideals, the entire ring and literally just the 0 element. Kind of nifty. Whereas the integers, where the integers have a lot of non-units, particularly the only units in the ring of integers, or plus or minus 1, the integers are allowed to have a lot more ideals because you can have elements within your ideal that are not 0 and also not units. So, boo. So, I want to talk briefly. What are we doing on time? 30 minutes. You know what? I'm going to be nice and let you go for today. Just because last class was a little bit longer. Thought I'd keep it a little bit lighter this time. So when we come back on Monday, we're going to start talking about different types of ideals within rings, namely principal ideals, prime ideals, maximal ideals, ideals generate cyclic ideals, ideals generated by a set, and more. So see y'all on Monday. Hope y'all have a good weekend. I hope you're all staying sane and healthy and happy. I mean, you all are cool people. I miss this class. in person. On Monday, we're going to have another group meeting. Had a fun one Wednesday morning. We kind of did talk through a couple examples. I encourage you to swing by Monday morning at 11 if you can, and we'll do some more crazy stuff, some examples and such. Optional, but it'll be fun. Have a good one, everybody.